Today I'll be talking about the approach we have taken to deal with poor code analysis support in our generator metaclasses and code generation heavy project. So we have open sourced a library that's called Toloka Kit. It's a Python library used to interact with our platform. And at some point, we started using some advanced features of Python, some dynamic features like, again, generators, metaclasses, and code generation. And we encountered some problems with IDE support. So I will try and explain the problem on a simple example. So say we want to create a module that's called sleepy, and we want it to contain a single function sleep4. So the difference in sleep4, the difference between sleep4 and the standard function sleep is that sleep4 accepts two arguments, the amount and time unit. So we can say sleep4 please 1 minute, half a day, or 2 weeks. And as we can see, if we are trying to use the function in some other module, we can see that our IDE, by the way, for the purpose of this talk, I'll be demonstrating everything on my PyCharm IDE, but effectively this should be the same in all other IDEs. So in my PyCharm IDE, we can see the signature, we can see the name suggestion for our arguments, and if we pass an unexpected argument or a wrong argument that does not fit our signature, we see that IDE highlights the wrong argument. But let's add a simple decorator. So let's add a decorator that logs function call. Typically, you would write the decorator like this. So this is a simple decorator that logs some string when the function is called and logs some other string when the function is finished. So we configure the logging, we run the code, we see that everything works. But let's have a look at the IDE support after we have applied such a decorator to our function. We can no longer see syntax signature. We can no longer access the argument suggestion, and we can pass an unexpected argument, and this will not be highlighted by our IDE. All gone. But signature is actually still there. So if we import an inspect module and we print the signature of the sleep4 function, we can see that the signature is still there. So why the IDE does not show us any suggestions? What went wrong? Well, the thing is that IDE uses static code analysis for its hints. It is afraid to run our code because it may have side effects, or because it may be badly written and raise an exception, or it might be a code in the middle in the process of being written. So it might not be syntactically correct, and IDE still has useful output. So the IDE tries to get as much to know as much as it can about your code without actually running it. And this is a tremendously hard job. Some IDEs might do better, some might do more poorly. But what can we do with this? Particularly in this case, we can, well, generally it's a good idea to provide your IDE and the static analysis tools with as much information as you can. And in this particular case, you could add an additional type hints that would tell our IDE that the decorator returns the same type as it accepts. And at least for my PyCharm version, this does not fix the issue with signature, but we can see that if we try to write an argument, we have the suggestion, and somehow the signature is in a pop-up window right above. Again, somehow it does not highlight the unexpected argument, but technically we can see that it might be some minor bug. Still, all the information is picked by the IDE. But not all cases are as easy as this one. As we can see, even a simple decorator can confuse the IDE, but there are harder ones. So let us say that at some point our user that used our Sleepy module returned to us with the feedback that they no longer want to use the time unit minutes or the time unit enum, because they do not want to write an extra import and time unit dot minutes or time unit dot hour is a long string to write. So they want to write units as strings. So what we can do, we can write an additional decorator that would take any function and try to cast all the past arguments to enums if need be. So we would add an autoenum decorator, and the autoenum decorator would look something like this. Let's quickly go through the definition. So first of all, we take the original signature of our function. Then we create a wrapper function that accepts args, quarks, and in order to map the original arguments, past arguments to the original ones, we bind the arguments to the signature. Then we go through all the arguments, and if we see that in the original signature the argument was annotated as enum, and the past argument is not an enum, we try to convert the past value to the enum type. And then we have quite a lot of code that preserves the original signature. So we take the original annotations, and if we see an enum somewhere, we replace this with a union of a enum and a literal that contains all the possible enum values. Finally, we assign the signature to the wrapper function and return the wrapper function. So as we can see, the IDE does not pick the updated signature. It highlights our units passed as a string, but both functions work. And if we output the signature that we obtain in runtime with an inspect module, we can see that the signature is correct and is present. As we can intuitively understand, the static code analysis tools would not be able to recreate the signature just by looking at the code without running it, because if I go back a few slides, we can see that this is pretty much an arbitrary code, and being able to understand the output signature of this function would effectively equivalent to actually running the code, and IDE and static code analysis tools do not want to do that. They are afraid to do that. So how can we fix the situation? We can fix this with stub files. Stub files is a language feature that was introduced in PEP 484. And long story short, it's a substitute for your original files. So for code analysis tools, you can say that for these tools, please, instead of the original file, take all the information necessary for static analysis from a substitute file that is called a stub file. So what should you put in a stub file? You should put all the public member definitions that were in original files, annotations, docstrings, final function signatures without decorators, constants where possible. If it's too complicated or impossible, you can use 3 dots instead. and all necessary imports for the code to be a valid Python. What can be omitted? Private members, decorators, and function implementations. So for our init.py, we would create a stub file that would look something like this. So we had a sleep for function, and we replaced this with a definition of sleep for function with the final signature. We omit all the implementation, and we keep all the classes and imports that are required in order for this to be a valid Python. So we imported an enum in order to be able to define a time unit as an int enum, and literal and unions from typing module in order for our annotation to be valid Python. The convention says that stub files are the files that have the extension PYI, and they should be called the same as the original files. In PEP 561, there was an addition that requires us to add a marker py.typed file to the module if it supports typing from type hints. So we do this, and this fixes the issue. So we can see the signature again, we can see the auto suggestion, and we can see that IDE highlights unexpected arguments. And also it does not highlight our minute string. So everything is okay, but now everything runs. But now we have a problem, and the problem is that we actually have to maintain all the PYI files manually, and this is quite a burden. So the approach we took at Toloka is automatic stub generation. The idea is the following. So static analysis tools are afraid to run the code, but if we know that our code is pretty much runnable, it does not have side effects during import time, does not raise exceptions, we can do the running part ourselves. So we can import the module, we can get the runtime module object, and from this runtime object, we can recreate this, create the stub files. So this would look something like this. This is a simple example that does not produce working output, just in order to understand how this approach works in practice. So we would write a file that would go like this. We would define a function that can create a module object from a given path. In the function that generates stub content, we would go through the module object, and we would traverse all the attributes and pick only, for this example, functions that are defined in this module. We would write a definition that would have a name, a signature, and an empty body. And we would run this on module. So if we run this, we get something like this. If we refactor the code, it would look something like this. So the problems that occur during the stub generation process are that we have to import everything that is referenced by the functions or the classes or whatever we are generating. In this case, we have to import unions. We would have to create the time unit. We would also have to manage the default values representation. This is manageable, but takes a bit more lines of code. And we implemented our internal tool for exactly this purpose. And if we run our internal tool on this code, it produces the following results. It generates all the necessary stub files. It generates the doc string for time unit, because actually when you create an enum class, it automatically contains an enumeration doc string. So this is taken from, everything is taken from runtime and generated automatically. For the autoenum and log function call, we also produced valid stub files, but they are not very interesting. So we are intending on open sourcing this tool later this month. This point, if you are interested in having a look at the original project where we used this approach to generate stub files, you can follow the link, and thank you for your attention.